80 million years ago, the coastlines of North America were dominated by dense monsoonal mangrove swamps. Heavy rains and thick fog blanketed these flooded forests, creating a vast network of murky, low-visibility estuaries. While the dry inland plains were the hunting grounds of early tyrannosaurs, the coastal wetlands belonged to an entirely different class of predator. At 35 feet long and weighing up to 8 tons, Deinosuchus was one of the largest crocodilians to ever exist. It dwarfed modern saltwater crocodiles and rivaled the mass of the largest terrestrial carnivores of its time. Navigating beneath the surface of these brackish waters were large, heavily armored prey. The prehistoric side-necked sea turtle, Bothromes, spent its life foraging in these channels. In an environment where visibility was near zero, survival meant moving without disturbing the water. The turtle's strategy relied on a slow, deliberate cadence to minimize its physical wake, attempting to slip past predators undetected. But Deinosuchus possessed a specialized biological countermeasure. Its skin was embedded with integumentary sensory organs, a network of highly sensitive nodes capable of detecting microscopic changes in water pressure and low-frequency vibrations. This sensory array bypassed the visual limitations of the silt and mud. It allowed the predator to map the exact trajectory of its prey using the water's displacement, tracking the direction and distance of an animal even when it remained completely out of sight. When those sensory organs registered prey, the predator initiated a strike. Propelled by lateral undulations of its massive, muscular tail, this motion generated an explosive burst of thrust from a depth standstill. The sheer bulk of the animal made sustained chases impossible. Instead, its anatomy was optimized for sudden, straight-line acceleration, closing the gap in a fraction of a second before the prey could react. At the moment of impact, the jaws snapped shut with an estimated force exceeding 100,000 newtons, trapping the armored turtle shell within an inescapable grip. This sequence of sensory detection and sudden acceleration functioned as a physical trap. The thickest keratin and bone armor available to late Cretaceous prey offered zero protection against that initial impact. Generating 100,000 newtons of bite force presents a significant biological problem. Impacting dense bone or shell at those speeds should realistically shatter a predator's own teeth and fracture its jaw. This cross-section of a Deinosuchus tooth reveals the anatomical solution. Unlike sharp teeth, these are thick and blunt for durophagy. Internal bands show multiple replacement crowns stacked inside, acting as shock absorbers to prevent fractures while exposing fresh enamel. Paleontologists have recovered extensive fossil evidence from the eastern coastal habitats of North America that demonstrates exactly how this biological engineering was applied to local sea turtle populations. This fossilized turtle bone displays the physical proof. The surface is marked by deep, circular indentations that perfectly match the robust profile of a Deinosuchus posterior tooth. These concentrated puncture marks show an animal designed to exploit the most heavily armored prey in its ecosystem, mechanically failing shells that deterred every other predator. Moving inland from the deep estuaries, the environment shifted into coastal floodplains governed by seasonal monsoons and periods of severe drought. As the dry seasons progressed, shrinking waterholes concentrated the local fauna. Massive herds of hadrosaurs and early tyrannosaurs were forced out of the plains to drink at the water's edge. This dinosaur bone fragment provides direct evidence of what happened at those shorelines. A singular bite mark aligns perfectly with the dentition of Deinosuchus. The crushed, unhealed bone matrix inside the pit indicates the strike occurred near the time of death, consuming multi-ton herbivores. Overpowering a multi-ton dinosaur requires immense physical bulk. For a cold-blooded reptile, achieving a body mass of up to 8 tons presents a massive physiological challenge. Paleontological growth ring data indicates that Deinosuchus underwent rapid expansion in its first 10 years, growing roughly a foot per year. By sustaining this growth over a lifespan of 50 years, the animal achieved gigantothery, a state where its sheer volume insulated it against temperature fluctuations. Decades of relentless biological accumulation allowed this predator to step outside the standard limitations of its physiology. It grew large enough to consume the apex predators of the land. Yet the reign of Deinosuchus ended millions of years before the asteroid impact that wiped out the non-avian dinosaurs, and it was never replaced by a superior competitor. Instead, the fossil record tracks a slow, millennial-scale shift in the global climate. Towards the end of the Campanian stage, average temperatures cooled, leading to a significant drop in global sea levels. This cooling directly impacted the geography of North America. The Western Interior Seaway, along with the vast network of coastal megawetlands, began to recede and dry out. Without deep, murky estuaries to conceal its approach and support its immense weight, the predator's greatest evolutionary asset, its 8-ton bulk, became a fatal liability. As the waters drained, the giant simply starved out of existence. Today, the physical remnants of these coastal leviathans are still being carefully excavated from rock faces across North America. Massive, deeply pitted osteoderms and shattered, tooth-marked bones. These remains document a predator that achieved dominance through specialized anatomy. By combining acute pressure sensitivity with mechanical force few bones could withstand, Deinosuchus effectively controlled the interface between land and water.